Hi, everybody. My name is Han Fosselman, and I am going to do my presentation on my undergraduate research fellowship. So the research that I did under the undergraduate physics fellowship focused on a uranium database and compound synthesis. The graduate student who I worked with was named Christopher Broyles. The postdoc I worked with, his name is Han Siddiqui, and my research advisor is Dr. Sheng Ran. So my database work took up weeks 1 through 5, and I'm going to tell you a little bit about how that database process worked and why it's important. So the database is over 800 compounds in total, with 500 compounds that have online data and 300 more that have no online data. Either that data was unavailable to us, or it was from the 70s and there was no online publication. So we spent 5 weeks on this because we don't know what we don't know. And basically what that means is that we know that there are gaps in this research of uranium superconductors, but we don't know what those gaps are necessarily. And so our aim to fill those gaps is to create a knowledge of what the gaps are. And there's a wealth of information that now that my PI is able to reference, and it focuses our research. So we aren't just randomly guessing what might be a good superconducting compound. And my role was to compile and do research for the database. This meant that I was reading lots of papers every day and looking at an Excel sheet quite a bit. And Sheng's role in this research was deciding what compounds were worth synthesizing, basically what compounds might be a good superconducting candidate, and why. So this is a sample of my work. You can see here I've put the labels of compound, transition type, TC, lowest temperature, and specific heat, structure, and then some notes. So to explain all of those, the compound is just the name of the compound. We focused on uranium compounds again, because Sheng believes these are a very promising material for a specific type of superconductor, which is high TC, meaning that it occurs at over 77 Kelvin. And then the transition type, we have abbreviations here. So PM stands for paramagnetic. And basically this means there is no transition type. And what that means for superconducting is that it might not disrupt the superconducting arrangement of the electrons, and magnetic ordering tends to do this. So it's important that we know what compounds are magnetic ordering and what compounds are not, because the ones that aren't might be good superconducting candidates. And then the transition temperature, TC, obviously because there is no transition, there is no TC for paramagnetic compounds. But if, for instance, this said antiferromagnetic or ferromagnetic, there would be a transition temperature or a TC. And then the lowest temperature measured, this is relevant because a lot of these compounds, when they were first studied, we couldn't get down to like 2 Kelvin, for instance. So 77 Kelvin is the temperature that we're looking for it to be below. And if they haven't been studied beneath this temperature, we know that there is a gap in the research, and we aim to fill that. The specific heat is relevant because it indicates whether a compound is heavy fermion or not. And basically what that means is that the specific heat has a predicted value at low temperatures. And in a heavy fermion compound, there are much higher. The specific heat is much higher at low temperatures than expected. The structure type, this is just the space group that the compound is a part of. This is relevant for superconducting in that it allows the electrons to flow in a certain way. And then just different notes on each of these compounds. You'll notice that some of these are highlighted in red. We have done that, Sheng does that when the compound is particularly interesting and one worth synthesizing. So as you can see, we have quite a few compounds we're synthesizing here and some that are not interesting. And we take notes on the interesting ones as well as potentially interesting ones. So my synthesis work took up the weeks 5 through 10, and I'm going to tell you a little bit about what I did and why it's important as well. So I spent 5 weeks on this because there are novel compounds that we just have never been synthesized before. There is no online data about them. There's no written data about them that we can find. And so it's very important to look at these compounds and study them in order to potentially find high TC superconductors. And it paves the way for other research. If we know how to synthesize a compound, we know how to measure the compound. Not necessarily we know how to measure, but we are able to measure the synthesized compound. And it allows interesting compounds to be measured, which is very important in determining their properties and potentially finding these superconductors. So my role is to make the compounds, and Chris and Hassan, the graduate student and the postdoc student, their role was to prepare and measure the compounds. So I have a list of the compounds we synthesized. We attempted about 40 compounds, including UTE, a couple of different uranium and magnesium compounds, and then ytterbium copper phosphide. And we succeeded in making about 20 compounds. So you'll notice that's about a 50% success rate. This is pretty normal for compounds that we don't have any information on and have never synthesized before. So I'd say we did pretty good. And then we succeeded in making some interesting phases of uranium compounds with nickel and cobalt, and then molybdenum boride, which has some interesting magnetic properties, and then uranium tin 3 and uranium indium 3. We actually made those while trying to look for something else. So you can see sort of that process of science and the happy accidents that occur. So here are some of the compounds that we synthesized. These three, the first one, the second one, and the fourth one, are actually all the same crystal. I believe it's uranium cobalt 2 tin. And it's this thin needle-like crystal. And you can see that we took this picture through a microscope. So it is quite small, but it's actually visible to the naked eye as well, which is pretty impressive for this crystal synthesis process. And just we took pictures of it at different stages of the process. So on the fourth picture, you can see this is just the raw crystal. In the second picture, we're able to glue it down to polish it. And then this first picture is completely polished. And then this crystal in the third stage is UTE, which actually this specific one Chris made, but I was also working on that process to synthesize UTE. And it was just a really good picture of a crystal, so I wanted to include it.